Welcome to Spring LIB.
In this exercise, a boy who's standing 2.5 meters above a swimming pool throws a rock up with an initial speed v0 equals 4 meters per second and an angle of 60 degrees. And the rock makes its trajectory as a projectile until it reaches the pool. And after it reaches the pool, the speed of the rock inside the pool is halved, and the direction and angle of the motion of the rock is the same as it was when the rock first touched the water. And the depth of the water is 3 meters. And what we want to find is the total time of travel for the rock between its releasing from the hand of the boy and it's reaching the bottom of the pool. Okay, so first of all, what I'm going to do is to divide the rock's trajectory into two parts. First, the part where its trajectory is a projectile, that is between its releasing and it touching the water, and then the trajectory of the rock inside the water. So first of all, I'm going to calculate the time that the rock spends on air. And for that, I'm going to use these equations that are highlighted in red. So the first thing I'm going to do is to set up a coordinate system. So the coordinate system I'm setting up is right here. It has the origin exactly at the place where the rock was thrown. And for that reason, y0 and x0 are 0. And for that reason, y is equal to v0 sine of 60 times the time t minus 1/2 of g t squared. And we want to find the time when the rock reaches the water. And the water is located at y equals minus 2.5 meters. So I'm going to substitute minus 2.5 for y, and this is equal to 4 times the sine of 60 times t minus 1/2 of 9.8 t squared. Everything here is in the International System of Units. So this is 0 is equal to, I'm going to multiply it all by minus 1. So this is 4.9 times t squared minus 3.46 times t minus 2.5. And then we can solve this formula. I'm going to write it as at squared plus bt plus c. And the solution of this formula is given by Bhaskara's equation. So this is minus b, which is 3.46, plus or minus the square root of b squared, which is 3.46 squared, minus 4 times a times c, and the minus contributes for the plus here, divided by 2a, which is 2 times 4.9. Notice that the minus solution gives a negative time, so we're not interested in it. We are only interested in positive time. So t is equal to 1.15 seconds. And this is the time it takes for the stone to complete its projectile trajectory. And now what we need to calculate is the time that the stone spends inside the water until it reaches the bottom. So first of all, we have to notice that the speed of the stone after it enters the water is 1/2 of the speed it had right before entering the water. So we have to calculate what was the speed Vf of the stone right before entering the water. And what I'm going to do actually is to calculate the speed in the y direction. Okay, because since the angle, since the direction of the movement of the stone is the same, then the total vector velocity Vf is equal to 2 times the total vector velocity Vw, that represents the velocity of the stone inside the water. So for that reason, I can separate the two components, and Vwx is equal to 1/2 of Vfx, just as Vwy is 1/2 of Vfy. Okay, so now I can calculate Vfy, and this is V0y minus gt. V0y is V0 times the sine of 60 minus gt, and this is 4 times the sine of 60 minus 9.8 times the time we calculated, 1.15. So Vfy is equal to minus 7.81 meters per second. So the speed of the stone inside the water in the y direction, Vwy, is 1/2 7.81, which is minus 3.9 meters per second. And we know that the pool is 3 meters deep, so the time t2 it takes for the rock to reach the bottom is delta x divided by delta y, which is the depth, divided by Vwy. So this is 3 meters divided by 3.9 meters per second. I just put the magnitude here because we're not interested in negative times. So this is equal to 0.77 seconds. So the total time, t, delta t, I'm going to call delta t, is equal to t plus t2, and this is 1.15 plus 0.77, and this is 1.92 seconds. This is the total time between the rock is released from the boy's hand until it reaches